Okay, we'll be conducting the proceedings in English, I assume. I could try in French, but it might take a little bit longer. My name's Simon Watson. I'm Professor of Wind Energy Systems and the Director of the TU Delft Wind Energy Institute at TU Delft. And it's my pleasure to be the President of the jury for the defence of Paul Mazoyer, who will be presenting his work today and will be examined by myself and the rest of the jury. So you can probably see on the screen over there, those of you alive in the room today, the members of the jury. We have, apart from myself, Sandrine Aubrin from the École Centrale de Nantes. We have Carlo Batasso from TU Munich. Yeah. Lars Lamberg from the NVGL. We have Valérie Mombet from the Université de Rennes. Yeah. And myself, of course, Andreas Bechmann from DTU. Andreas there, yeah. And then obviously locally here we have George Kiriniatakis, who's in the room from the university here. Okay, so the way the defense will be conducted, first of all, Paul will give a 45-minute presentation of his work. And then there will be some time for members of the jury to ask some questions. So Sandrine will ask questions as the rapporteurs, and Carlo as the rapporteur. They'll have some time to ask some questions. They'll have the most time. And then the remaining members of the jury will have some time. There's also some time at the end for members of the audience, but only those who have a PhD, apparently, to also ask a few questions. Okay. Have I missed anything, George? Is that right? That's fine. So I'll hand over to you, Paul, to give your presentation. So 45 minutes. Okay. Thank you very much.
Thanks a lot, Mr. President, for the introduction. I'm going to present today my work on the development of a method for assessing the wind energy potential of a repowered wind farm. That work was conducted at MinParis PSL in the Center per se, with an industrial partner, NG Green, and with another academic partner, DT. So my presentation is going to be in 5 parts. I'm going to start with the context and objective. We'll see after the models. We'll discuss with the existing models. Then I will introduce a model that I created during the PhD. I will discuss the specificity of the model dealing with the input variables, and I will conclude. So with no further ado, the context and the objectives. There are high ambitions of installation of wind power capacity in the world. We are targeting 2,000 gigawatts by 2030, and to keep up that capacity growth, to do that capacity growth, we have to look at the equation here. So we try to add new capacity to the grid, but this is either doing greenfield development, which might be more and more difficult due to weak local acceptance, to land access difficulty or rising cost. And on the other hand side, what limits the capacity growth is the fact that after 25 years, the wind turbines, they cannot operate any longer safely. So we have to decommission them. They come to their end of life. And there is a massive capacity which is close to this end of life. So it opens a new possibility to add new capacity to the grid, which is called repowering. So what is repowering? What is repowering? It's an end-of-life option that consists of, instead of dismantling an existing wind farm and giving back the land to its initial purpose, it consists of building a new wind farm instead. So it's basically replacing an old wind farm close to this end of life with a new wind farm. From the developer standpoint, point of view, it comes with a lot of benefits. First, we benefit from a good local acceptance because the wind farm is already built and the communities got acquainted with. Second, we can reuse the existing infrastructure, and this leads to reduced cost in the development. And finally, it also comes with higher reliability and capacity. The new wind farms are better because the new wind turbines are better. When we do a repowering project as wind farm developers, it's exactly the same as when we do a greenfield project. We need to assess the risk of the project. We need to be able to tell whether the project will be profitable or not. If it is profitable, we'll go for it. If it is not profitable, we don't go for it. And the main uncertainty, the main risk that we have on the project is on the resources. The resources, the wind resources are hard to qualify, and it leads to a high uncertainty on the production of the wind farm, and then a risk for the project. So the decision-making process for wind farm investment, whether repowering or greenfield project, is always the same. First, we gather site data, wind measurement, topography, and so on. We perform a yield evaluation. We predict the energy yield of the wind farm to be installed. We design the wind farm accordingly. And then we perform an investment decision. So we've done that for the existing farm. And the question is, why should we reevaluate, since we have already done that for the existing farm, why should we redo it for the new wind farm? The thing is, the data that we used, they date back before the installation of the existing farm, so generally 25 years ago, so they are not of very good quality. And the tool that we use, they have evolved in the past 25 years as well. And also, last point, the new wind farm is most probably very different from the existing wind farm. So at this stage, my PhD will focus on that point, the yield evaluation that is in yellow here. So how should we do a yield evaluation for the repowering of wind farm? So how do we do now? Now, within the wind industry, we use a physics-driven model. We gather site data. We use weather or climate data with a coarse resolution, but which are of long-term historical data. And we input the farm configuration as well. We perform a wind resource assessment, which consists of translating that data into data that are representative of the wind speed and wind condition at the wind turbine location and at the hub height. And we also model the conversion of wind resources into power through the power curve. And then we simply calculate the average of the power curve over the wind condition, multiplied by a scaling factor, and we obtain the EP. The thing is, that method, which is a standard, the baseline method within the wind industry, it comes with an error from 6 to 12%. The error can increase if the site is more challenging, such as a complex site in hilly or mountainous site and so on. Still, the range of error is that. So what we want to do is we want to look and investigate method to do assessment better, that error is lower than these errors. And what is new in the context of repowering is the fact that we have access to the historical data of the operational of the existing farm. So we can augment the physics-driven model with data. I could also investigate those models here, improve them, but the angle of attack of this PhD was to try to use the historical data of the existing farm to improve the physics-driven model through data augmentation. It comes with 3 challenges. The first challenges, which is a well-known challenge, is that those data here, they can be of bad quality. And the wind farm may operate very far from its... Oops. The wind farm may operate very far from ideal operation. The second challenge is to extrapolate the information that we gather at the historical existing wind farm to the new wind farm. If the existing wind farm is 40 meters up height wind turbines, and we want to model a wind farm with 80 meters up height, there is a discrepancy that we need to bridge to gap between the 2 wind farms in terms of representativity of the data. Second, the method should be practical for industrial application. We cannot come up with a method which is too complex and too expensive. And third, obviously, we need to beat that typical error of the PDM. So the main 3 questions that I want to answer in the PhD and in this presentation is how to integrate the historical data in the process. What is the added value of doing so? So can we do better than the PDM? And can we do that within industrial constraint? So the overall objective is to develop a method for energy assessment wind farm, considering the data of the existing farm while respecting the business requirements. And I'm going to answer that objective in 3 parts. First, assessing the existing models. Second, coming up with a new model which address all the challenges that I have listed before. And then dealing with a specific issue that I will introduce here, the modeling of the input of that model. So first point, assessment of the limitation of the state-of-the-art model. So the first thing that was a bit challenging when I started the PhD is that there is very few papers on EYA for repowering, so EYA energy yield assessment. And I could classify, there is about like 10 papers dealing with that topic, and sometimes they are not really focused on that. It's a side project of the paper. And I could classify those methods into 4 categories. So, and I could scale those methods in a scale of industrial constraints. So here, the industrial constraint is not match, here it is match. And in terms of added value, so here, very low added value, high added value. I won't describe everything. The thing is I could identify by reviewing the method, not testing the method, but just reviewing the method, that the most promising method was the adjustment of the PDM that I'm going to show later on. So it's a choice I made at the beginning of the PhD to focus on that method. I could have choose to focus on other methods, but I wanted to dig into one method to be able to understand it the best. So I choose the adjustment of PDM. So what is the adjustment of PDM? Here, the two squares, they represent the existing wind farm and the repowered wind farm, so the new wind farm. So this is a fictional ideal world in which we model the AEP through the PDM of the existing farm, and we have access to the operational data. We perform an operational assessment, which is basically treating the data, removing anomalies and so on, to obtain the realized AEP out of the operational data. And then we can make a link between the PDM assessment and the realized AEP. That link is a scaling factor called K existing, which basically represents the error of the PDM, which permits to link the PDM to the true AEP, the ground truth. Imagine we have the same for the repowered farm. We have the same chain, model chain. We model the AEP. We have the operational data. We have the realized AEP, and then we can just calculate the scaling factor K repowering. The thing is, we don't have this data because the new farm is not even built, so we don't have this data. So we don't have K repowering. This value, we don't have it. However, what we can assume is that the K repowering, we can use instead K existing. So we will not get the realized AEP, but a value called adjusted AEP. And if K existing is equal to K repowering, then this is equal to the ground truth. So that's the baseline reasoning behind the adjustment method that I'm going to further discuss in that presentation. Just to make the thing extremely clear, let's work out a small example. Say we have a wind farm, we model the AEP, it gives 10 gigawatt-hour per year. We took the data, we make an operational assessment, we come up with 11 gigawatt-hour per year. So the K existing is 1.1, right? Now, we do the same, we model the AEP for the repowered farm. We say we obtain 15. Then the adjustment method says that we will have, one prediction of AEP, one assessment of AEP is 16.5. So we have one estimation coming from the model and one other estimation coming from the adjustment method. And the question is that estimation good? And we see that for that estimation to be good, we need the adjustment assumption to be true. So the overarching objective of that part is to verify that the adjustment method assumption holds, that it is true. To do so, we will gather a real-world dataset of repowered wind farm. So this is like, we are no longer in the context we are planning to build a repowered wind farm. We'll be in the context where the repowered farm is already built, and we have operational data from the repowered farm, from the existing farm, so we can compare the prediction. So we will gather that data set, we will model the AEP using a PDM for both, and we will validate experimentally the assumption. What we want to do ultimately is that, answer that question, is it equal? So with respect to the dataset, it was a bit complicated. I did not have access to repowering datasets, so I use extension of wind farm. Extension is basically the principle of you build a wind farm, few years after you figure out that you could build another wind farm very close by. So for example, here initially ENGIE built these farms here, and they figured out 5 years after that they could also access this land here, so they built wind farms here. And in the following, I will consider that the wind farm initially built is the existing farm, and its repowering counterpart is the extension that is here, all right? So it's not repowering per se, but it resembles a repowering. We can also see on these graphs that we have access to a mast, which is located here in red, and there are also other wind farms that we should take into account. So I have 3 use cases. One use case represent an augmentation significant of the rotor size with keeping the same hub height. The second use cases represent an augmentation of the rotor size plus an augmentation of the hub height. And the third cases is like you have, it's a similar wind farms, though of different turbine makers. The wind resource assessment models that I'm going to use, so the power curve, I'm going to use an EC model. The air density, I'm going to use just the air density from ERA5. And the wind resource assessment models that I'm going to use in the entire presentation is that one. So the historical data is ERA5 downscaled with the WRF, so mesoscale model. I'm going to use the mass time series available for each use case. The vertical extrapolation, I'm going to do it with a power law. I'm going to do an MCP using either k-mean or random forest with several predictors. The flow modeling is done with WASP, and the wake modeling is done with the Jensen model. So at the end of this wind resource assessment flow chart, we get the effective wind speed for each turbine location at the right hub height. So let's delve a bit into the results. So let's start here. So here it's named PDM error. Remember that K factor that I presented, the K that I want to validate, and PDM error is basically the same thing. They're just a -1 component between the two. So here we will focus on the K value or on the PDM errors. It's the same. So what we can see when we look at the PDM error comparison is that or the K factor basically, is that the K factor for the old and the repowered farm are very different. For the first case study, we can see that there is almost a 0.9%, 9% difference. And there is only one case for which it works well. So that was a bit problematic because if we just look at the results here, we cannot validate the adjustment method assumption. So we looked at the yearly evolution of the K factor, or in that case of the PDM error. So that scale represents the PDM error, but again is the same as the K factor. What we can see is that when we plot it with the date in years, we can see, for example, for case study 2, that there is a pattern of declining error. However, there is a temporal shift between the two. Here we can see another phenomenon. One wind farm, so this is a case study 3B, 3E, and this is the existing farm PDM error. Well, we can see that there is a good match here, but here there is one PDM error which is very far from the PDM error for the other farms. And here we have a very high PDM error, which is mainly due to the fact that I use a very poor quality input data just to test the method, to challenge the method. So if we change this axis and we consider no longer the years, but the operational age, so the age of the wind farm, we can see that for the case study 2, what has been very shifted is now synchronized, and the red and the purple curve, they kind of overlap. The operational age of the 3 wind farm were the same here, so it didn't change a lot. And for that farm here, when we change the operational age, we can see that the green point become very close to the orange point. However, there is only one observation, so care should be taken with the statistical uncertainty here. So when we re-average on the period corresponding to the corresponding operational age, we find way better results for all wind farm, except for one, for which we still have a large difference. So what happened on this farm? So this is the same graph, the PDM error that I just showed before. So bear with me here because it might be a bit complicated, but here the red curve represents the PDM error evaluated for those 4 wind turbines here. The green curve represents the PDM error evaluated for this farm here, And the old existing wind farm that we use to calibrate the process is all the hard blue points here, and it's represented in purple here. So how can we explain such a shift? We looked at the power curve. So here is a plot of the power curve from the NASA anemometer in thin curves, and the thick curve represents the warranted curve. So the curve that has been tested on site. So it's basically the nominal performances is that purple line, and the observed on-site performances are those one here. And here you have the wind speed and the power. So normally those should match. And what we see is that for case study 3E, we have a good match, almost a good match between the observed power curve at site and what we should basically have. And for the case 3B, we have a large discrepancy. So it's very likely that this PDM error here, which is very different from the other, is explained by strong and systematic underperformances at the site. And we don't observe that for the other wind farm because there is a good match. So what are the takeaways from that first part? The adjustment method, it proves accurate. So the K factor are quite equivalent, or the PDM error, again, it's the same thing. But there is a focus needed on looking at the performances. And that we already have tools for that. Also, it more comes as a recommendation to the wind industry to use the tool available for looking at the performance. However, now that we have found that, we can still see that there are few challenges that are not addressed by the adjustment method. So we address the performance issue. It's very easy to use, so the practicality of the method for industrial application is addressed. However, if the input dataset is of bad quality, we cannot reflect this into the assessment. Second, if the wind farm is very different from the initial wind farm, we did not have a use case like that, so we don't know how the K factor will behave. And last, it does not come with an uncertainty prediction, that method. So we need to adapt it to have an uncertainty prediction. So that's why I developed a new model based on the adjustment method. So that's what I'm going to present in the part 3. So the idea is to, as I said before, deliver a prediction of uncertainty, assess the impact of bad operational data quality, and assess the impact of varying configuration between the old and the existing farm. And the methodology is to develop a probabilistic approach and validate it against operational data. So again, bear with me here. That's a new way compared to what I presented before of thinking about the estimation and the modeling of AEP. First, we take the data, we run it through the PDM, and we quantify the uncertainty associated to that prediction for the existing farm. So instead of getting one scalar value, we get a distribution of probability of obtaining such or such AEP. The similar, we have access to the operational data of the existing farm, so we can observe the AEP. And on the other hand side, for the new wind farm configuration, so using the same PDM with the new wind farm configuration, we can also model a distribution of AEP. And it's quite straightforward to use the Bayes theorem and to calculate the distribution of the new wind farm AEP condition on the observation of the AEP at the existing farm. And that goes through a joint probability distribution. So that's a key concept which is very important in the rest of this work. That joint distribution, what does it say? It says the probability of observing this AEP at this farm and this AEP at this farm together is that value. It gives the probability of observing similarly two events. And that permits to calculate the posterior distribution. We can also calculate, the basic principle of Conway is to build upon the PDM method and that distribution, and to add a layer, as we do for the adjustment method, to evaluate further the conditional distribution. That conditional distribution, we can also look at that conditional distribution, from a probabilistic point of view of the operational assessment. So the operational assessment is no longer a deterministic value; it's a distribution of observations. Why we do that? It's because if we have data missing in the operational data set, then the operational assessment will have a bit of uncertainty. So how can we solve that equation? So the magic of that is that this equation, which look rather complicated, find a very simple solution under Gaussian assumption of the joint distribution. So the posterior distribution is Gaussian as well, and the parameters are linked to the parameters obtained from the uncertainty quantification of the PDM, the operational assessment. The only thing that is a bit new here is the correlation of the AP, which is a variable which is quite new, and I did not find a lot of literature on that topic. So first we will try to evaluate what is the impact of this variable on the estimates and how to calculate it. I will address that point in the second part. Just a quick note, this is not a Gaussian process. So it might appear obvious that this should be solved through a Gaussian process, but this is not, and we will see why after. So to illustrate the impact of the correlation factor, we'll conduct a sensitivity analysis. Again, this is very simple. If you evaluate the PDM estimate here with an uncertainty of 1 gigawatt per year, you say you estimate 10. You have the operational data for the existing farm, you conduct the operational assessment, you find 9.25 plus or minus 0.25. You do the same PDM for the report farm. Since it is a bigger, larger wind farm, the PDM the AEP predicted is slightly higher, 20 plus minus 1.5. So the uncertainty is plus minus 1.5. Here we can evaluate the correlation, the impact of correlation onto the mean value and the standard deviation. And what we can see is that under those values, with those values, the Conway estimate, so which is the posterior standard deviation of the Conway estimate, the uncertainty decreases with evolving correlation value. And if we have a high correlation value, we end up with predicted uncertainty, which are very low, 0.5 gigawatt hour per year. That translates into a high financial benefits. Also, the mean estimate, it evolves with the correlation, value, starting from no update, so just taking the value as it is if the correlation is 0, as to a value of 19. And what does it translate that? It translates the fact that if there is a big correlation between the two farms' PDM estimates, then the errors that we have observed here, which is 0.75, should also be taken into account when estimating this AEP. But different to the adjustment method, we have an uncertainty quantified with that, which is contingent upon the correlation. Similarly, and this is a side note just to explain, this is not a Gaussian process. If the operational assessment, I miss a UQ here, sorry. If the operational assessment comes with a large uncertainty, we will take into account and transfer all the uncertainty on the operational assessment into the new prediction. So increasing correlation will provide an estimate with increased uncertainty, which is not what we want. So the operational assessment uncertainty is key in that process. And last point, if the estimate are similar, so if the PDM estimate match perfectly the realized production, then the mean won't change. The Conway mean estimate, it will be the same, whatever the correlation value, but still, even though we have the same value for the PDM and the realized AP, even though the PDM was perfect, we can quantify the fact that the PDM was perfect through an uncertainty reduction. So this is quite an amazing result because it shows that even when confirming the PDM, we decrease the uncertainty. So what we've seen so far is that there is a simple model for the AP assessment of the report farm, and we show that the sensitivity analysis, through the sensitivity analysis, there is an high impact of the correlation. The question is, how can we derive that correlation value? Long story short, what we can do is to write the PDM stochastic equation. So instead of just writing the PDM as I showed before, we can write the PDM with terms that correspond to the errors on the inputs. So namely the error on the wind speed, on the air density, and the power. And this, we write it in a joint manner. So we not only predict one AP, we predict conjointly both AP. then we have to, this is a key point, we have to evaluate the uncertain variable joint distribution to be able to sample those distribution. And then we need to propagate the uncertainty. So there is many ways of propagating the uncertainty here. And I choose the Monte Carlo sampling as a baseline method because even though it is very expensive, it's more precise than those other methods. So the way we do the input sampling, so this is a rather complex flowchart, but the idea is very simple. We use we input the mesoscale climate data as we would do for the PDM of the repowered and the existing farm, and we add uncertainties on the input data through a sampler of the uncertainty distributions, and that we repeat it over and over to obtain a significant sample of the AEPs. So this part is quite straightforward, and once we have sampled the distribution, we can easily calculate the correlation through the statistical correlation calculation, which is shown here. So the main complex part here is not to do that propagation, which is quite easy to do with Python, is to sample the input, to find the distribution, the joint distribution of error. And those input sampling, here is an explanation on how I did that. For the wind resource assessment uncertainty, so to find that distribution of joint errors over the existing and repowered farm, we propagate joint uncertainty at several steps of the wind resource assessment process. So we propagate measurement uncertainty, power law modeling uncertainty, MCP uncertainty, flow modeling uncertainty, and wake modeling uncertainty. The thing which is very new here is that it's not one-dimensional uncertainty. We propagate 2D uncertainty, so joint distribution of uncertainty. And we did the same for the air density and the power curve. There are not much literature so there are not much references, and each time I had to come up with a new model, apart from for the horizontal extrapolation, sorry, for which Clerc developed a joint uncertainty model, which I could use. So let's look at the results. So I just choose one case study here. So the case study that we have already discussed before, case study 1, and we evaluate in the stochastic manner. We evaluate the AP here, the AP here, and we represent it on this graph here. So here is a distribution of AP for that farm with the hard blue point, and here is a distribution of AP for this farm here. So very good news. First, the marginal distribution were Gaussian. So it verified the assumption that we made first, at least that the marginal distribution are Gaussian. And also, so you cannot see it here, but I ran a statistical test, and this distribution is also Gaussian. When we evaluate the correlation factor on that set of samples here, we find 84.7. Which is a very big result. So it's a very key result, that point, because it shows that you can explain the AP of a neighbor farm with the AP of that farm here. So both APs are linked. They have a strong correlation coefficient together, and it permits to predict one farm from the other. We also looked at linearization. I did not present it here, but linearization to calculate the correlation of coefficient is very efficient because, I mean, it's very efficient in terms of computation. And what we could show here, applying the linearized model, is that the correlation coefficients were quite close. So it's good for industrial implementation. So last part of this third part, we ran a comparative test. So what we did now is that we have verified the basic assumption of Conway and we are able to calculate the correlation coefficient. We took the 3 case studies that I have presented before. We ran the PDM, made an uncertainty quantification at the model AP, performed Conway and add the Conway EP. So we had 2 estimation of EP, and we compared for all the wind farm with the ground truth. So what do we find? What do we found? Yes, we found that for case study 1, Conway is very close to the realized production, but so is the PDM. So it's a kind of weird case because the PDM is already on spot. But what we see is that the Conway estimate is quite also close So it confirmed the PDM estimates. For the case study 2, which is a case for which the mass data were very bad, it's quite amazing, but the PDM says 55.7. The reference is 48, and we end up at 48 with Conway. So Conway is very efficient for the case study 2. And for the case study 3, it doesn't really work, which is an issue because we have like 20.9 realized AEP, 21.3 from Conway, and 20.9 from PDM. So in that case, Conway is less accurate. We kind of try to dig into that. So in red, you have the Conway estimates per years. In the green, you have the operational assessments of the ground truth, and in blue, the PDM. And what we can see is for 2 years, there is a big discrepancy between Conway and the ground truth, while the PDM is on spot, nearly on spot. So this is something I did not find any reason for that, except that the performance of the wind farm, of the existing wind farm, might be an issue in that assessment. So we demonstrated that Conway provides a simple and tractable solution to adjust the AEP of model by AEP. Sorry, it is accurate. However, we need to take into account the performance degradation, and the Conway output, it depends on the model that we use to calculate the correlation. And as I explained before, there are no models so far to do so. So I had to create models, especially for the power curve and vertical extrapolation, which come with significant impact on the PDM. So the last part, hope you got everything I said before, but the last part will focus on trying to find joint error model for the vertical extrapolation error. Although we should do it for everything, but I'm going to focus on that. So the last part is discuss the uncertainty analysis of the input variables. Whoops, sorry. So the objective is to design an uncertainty model in a joint manner for the vertical extrapolation error. And side objective are to demonstrate the efficiency of a maximum likelihood approach for uncertainty model calibration. We'll see why later. And also to evaluate the impact of measurement noise in uncertainty model calibration. And that I also explain why I add that to the objective. Anyway, the methodology is to develop the joint uncertainty model and to calibrate it against operational data. So as I explained, we should work on each of the source of uncertainty within the PDM. However, I could not work on everything and present everything. So today I will just focus on the vertical wind profile, the power law. But again, what I do here, I should do that for every uncertain variable within the process. So what are we dealing with? We are dealing with a very classical, very simple approach to surface layer modeling. The idea is that if you measure the wind speed at this height or this height, but the wind turbine is at this height, you need to extrapolate the wind speed. So there are plenty of models to extrapolate, but the most famous is the power law approach from Hellman. And this says that the mean wind profile follows a power law function. The idea here is to use those two measurement heights, extrapolate to one height corresponding to the existing farm, and to another height corresponding to the repowered wind farm hub height. And the idea is to see whether those errors that we make when extrapolating are the same. So if we define a joint, a couple of errors as the prediction minus the ground truth, what is the distribution of these errors? So we assume it's normal. Sorry, we assume it's normal, and the idea of this part is to find the mean value, the standard deviation, and the correlation. So how can we do that? The parameters, some of them are already known. For example, the variance parameter has been discussed in the Kelly paper back in 2019. The correlation has never been discussed. As I mentioned before, it's quite new to model joint distribution of uncertainty. So I assume the linear covariance model with parameter theta core and the heights. And for the function m, which is the mean of the error, I won't detail the candidate functions, just to mention that I tested several functions and several predictors within that function to capture the mean. And the idea of this calibration process is to gather representative data sets of the joint power law modeling error to identify a likelihood function corresponding to that distribution here. I mean, to link that distribution here to the observations. And that's where there is a tricky part, because when we observe error, it's not the prediction that we directly observe, but we observe it through a measurement error. So I had to include in the manuscript a term for the variance of the measurement error and also a term for the process. So this is what is a bit new in that calibration process. And anyway, the final idea is to optimize the observation based on that distribution here to find the best mean model M and to calibrate the parameters that I mentioned before. And to do so, we will use a genetic algorithm approach because it turned out to be the most efficient. So the case study, we had a 13 measurement campaign lasting for 4 to 12 months. And for each campaign, we have 10 different measurement heights. So we could calculate different couples of error. For example, U1, U2 extrapolated to here, or U2 or U3. So for each campaign, instead of observing just one couple of error, we can observe 100 of couples of error. So finally, what do we observe and what are our conclusions? We observe that the power law model error, PL, here, it evolves so with a coefficient that we call IR. IR is basically a proxy that indicates the complexity of the extrapolation task. So we can see that the PL error evolves with increasing IR values, and it's very interesting because as we can see it here from the mean in the dash line, it's positively biased. So it led us to calibrate the mean error using a second order polynomial with the interrange ratio and the shear coefficient, which I forgot to mention, which is in color here, and also turned out to have an impact on the PL error. So that's a very first interesting point because most of the uncertainty model, they assume unbiased modeling, and here it's not the case. It's biased and is strongly biased with ER increasing. Second, we run the calibration with that mean model form, and we could confirm the parameters from Kelly 2019. So this is a good thing. And last point, which is very, very important, we could calibrate a correlation. I mean, the calibration leads to a value of correlation between the measurement error of 92%, even for the case where the interrange ratio is high, which means the complexity of the extrapolation task is high. So what does it mean? It means that if you extrapolate at one height or extrapolate at the other height, it's very likely that you will make the same error. And while this seems obvious, it's key for the application of Conway because it drives the correlation value of the EP to be very high. So this is a very good result. By the way, we found the same result for the similar result for the power curve modeling, which I did not show here. So the calibrated uncertainty model is reliable. That we verify through calibration and show high spatial correlation of the power law modeling errors. So with that, I'm going to conclude. So what are the scientific contribution of that PhD, of this PhD? First, we validate the adjustment method as a baseline approach. So we did an experimental validation of the adjustment method, which and we showed that we need to focus on performance before, if we really want to apply this method, we need to focus on performance before applying it. And we also showed, I did not really insist on that point, but even when we have very low quality of input data, and even when we don't have mass data on site, but only ERA5 data, there is a high similarity of the PDM error. So the adjustment assumption is verified and we can use it. So it's a good thing to reduce the cost of development with low quality input measurement data. In the second part, we demonstrate the efficiency of a probabilistic AP estimator, and we validate the assumption that we could use Conway in the Gaussian version. So just use Conway with the Gaussian equation. And finally, we also implemented an interesting uncertainty quantification method using Monte Carlo, which has already been done in the past. What we worked on at the moment in the PhD was on the uncertain variable distributions. Last point, we developed an uncertain variable PDF model So we did it for the vertical extrapolation and also for the power curve modeling error. And this last point, which is a bit side to the PhD, but I'm very happy we found that. We also found that when we want to calibrate an uncertainty model, the measurement uncertainty of the reference should be taken into account because it changes otherwise a lot the results. So what else the industrial impact? The method leads to improved accuracy in energy yield assessment for repowered farm. We have improved the uncertainty quantification in wind power energy yield assessment, and we gave practical recommendations to explore operational data with respect to the performance of wind farm. There are limitations in the PhD work. It lacks extensive validations against operational data. We have no method so far to assess the operational assessment uncertainty. So this is an issue because I assume value here, but we need to further work on that to better understand this uncertainty. And finally, we are not really able to quantify the energy loss due to sub-performances. So this is still something that Conway cannot disentangle and can reduce the accuracy of the P50 evaluation. So the perspective, we should further validate Conway against operational data. There is a clear need for a work to review the uncertainty model for other uncertain variables. And Conway could be expanded outside repowering to predict, as I mentioned before, an extended wind farm from a wind farm located nearby. So with that, thanks a lot for your attention, and thanks a lot to NG Green, CIFRE, NDTU, and Erasmus+. Yes.
Okay, so as I said, we had a period of deliberation, and we have come up with our verdict, and we've prepared a script, which I will now read out. Paul? So, Mr. Paul Mazoyer gave the jury a very clear presentation, supported by very well organized and understandable slides. This presentation in fluent English complemented well the important work presented in his manuscript. The presentation gave an overview of the candidate's research related to the use of operational data in the assessment of the potential for repowering wind farm sites. In particular, the presentation covered the important elements of the work related to the incorporation of uncertainty into any assessment using a Bayesian framework. The candidate showed through his work how he combined mathematical theory and real-world data from a number of different wind farms and measurement campaigns to illustrate the validity of his approach. His work illustrated his ability to carry out advanced scientific research within certain industrial constraints and showed the real potential of the proposed method, called Conway, for use in future commercial repowering assessments, subject to further validation and industry acceptance. During a long session of diverse and searching questions posed by the members of the jury, Paul Mazoyer showed that he had a comprehensive understanding of his research field and the relevance of his research. He was confident and assured in all the answers, whilst being able at the same time to rigorously define the limits of his work. For all the reasons given above, the jury unanimously decided to award Mr. Paul Mazoyer the grade of Doctor in Energy and Processes of Paris Sciences and Letters University, prepared at Mines Paris, PSL, under the auspices of the doctoral school number 621, Ingénierie des systèmes matériaux mécaniques énergétiques. In addition, the conditions for awarding a European doctorate label have been met. Congratulations, Paul.